start in. Good morning, everybody. We will start in approximately 2 more minutes. Good morning, everybody. We're going to go ahead and start the webinar called Multi-Objective Optimization of Electric Motor Design using modeFRONTIER and JMAG, hosted by Esteco North America and Powersys Solutions, who is an agent for JSOL, the developer of the JMAG software. To start with some logistical topics, by default everybody is muted. If you have any questions, you can go to the chat box and type your question there. Make sure to send it to the host, and then later at the end of the session we will collect all the questions and have a brief Q&A session. I would like to welcome everybody for attending this webinar on behalf of Esteco and Powersys. We have the following 4 people online presenting today. Most of the technical contents will be presented by David Farnia from Powersys and Brandon Wagoner from Esteco North America. My name is Roel van der Veld. I take care of the business development in North America, and with me is also my colleague Sumit Parashar, who is the manager of the technical team in North America. On the agenda for today is a brief introduction to both companies, followed by the demo application case. Esteco is a pioneer in numerical optimization solutions, and we are specialized in the research and development of engineering software for all stages of the simulation-driven design process. Our vision is perfecting engineering and reducing complexity. The company was founded in 1999 as a spin-off from university in Trieste. It is an Italian-based company, and the first version of modeFRONTIER was developed in a European research co-funded project, which was very successful, and therefore it was decided to have a commercial spin-off. So the company has been around for almost 15 years now, with the North American office being incorporated in 2004, so almost 10 years ago. Currently, we have 3 Esteco offices, one in the US, one in Italy, and one in India. And in those markets, we take care of the distribution ourselves, and we work with several partners in other regions, being IDAJ for Asia, Enginesoft for most of Europe, and ESSS for South America. The customers we serve, you can find those in every sector, because optimization is a generic application. You see the software being deployed at over 250 customers around the world in the disciplines of aerospace, automotive, consumer goods, electronics, etc. A quick introduction to modeFRONTIER. What it is an integration platform for multi-objective optimization. What that is, you must be all familiar with a scenario where you have a certain design that has a certain baseline performance, and you know that by changing certain parameters you can either get better or worse performance. Manually, that would be a labor-intensive trial and error process, but by using smart algorithms in modeFRONTIER, you can automate this process, and the tool can find those maximums or optimums for you. Multi-objective means that you will have more than one objective, and these could be in conflict with each other. So the tool will allow you to select a set of optimal solutions that you as a designer can move forward with. It is also a platform for multidisciplinary design. That means that traditionally people were maybe focused on their own discipline, whether that was structural analysis, electrical analysis, but with the concurrent engineering being more popular these days, you have to go into MDO, multidisciplinary design, in order to make sure that whatever changes you make to improve your part of the product does not negatively affect the performance of someone else's component. In modeFRONTIER, you can automate that by having these different tools that belong to different disciplines link to each other and communicate with each other. So you can take the export from one application and feed that as an input in the next application, and all these processes are automated for you. And then finally, having a good solution doesn't mean much if you cannot really identify what that solution is. And with that I mean you need to have powerful post-processing capabilities to really understand what is your best design, what potential trade-off do I have, does it correlate or does it not correlate, what's the scatter of my data, for example, and that can be analyzed in the post-processing module of modeFRONTIER. These are the main components of the software. So on the process integration side, the modeFRONTIER software is very powerful in linking third-party commercial softwares, but also in-house written tools. We have direct integration with many of the most commonly used CE and CAD packages, but we can also, through simple command line, communicate with your own in-house tools if you have those. On the design of experiment side, we can use several algorithms to populate your initial design, and that can be used to as a starting point for your optimization. In the optimization side, we have about 20 different algorithms, varying from very basic to very advanced, and of course we will cover some of those later today. Response surfaces, they can be used to, instead of a direct optimization, as long as your correlation is high enough, you can use response surfaces for further optimization, and that gives you to a solution in a much quicker way. On the robust design aspect, if you know you have certain manufacturing tolerances on your product, you can assign those to your input parameters, and the tool will take that into account in its evaluation. And then finally, the last three belong to the post-processing part. That is also really one of the strengths of modeFRONTIER, and today we will show you different type of plotting capabilities. And then to start, or to stop my part of the presentation, here is just a quick snapshot of what a typical modeFRONTIER workflow looks like. From left to right, we have our what we call our process. So all the tools go from on the horizontal line, and on the vertical line we have our data flow. So we start by assigning input parameters, running it through the solver, reading the output, and then accordingly identify or assign constraints and your objectives, whether those are minimizing or maximizing certain parameters. That concludes my part of the presentation. I would like to hand it off to Dave now, who will provide an introduction to Powersys and JSOL and the JMAG software.
So Dave, you are the presenter. If you can share your application.
Yep. So hopefully, can you hear me?
Yes.
Excellent. All right. Well, as Roland mentioned, my name is Dave Farney, and I work for the JSOL Corporation in supporting the JMAG FEA software package. JSOL was established in July 2006 as a split from the Japanese Research Institute. JSOL is a relatively large company with about 1,300 employees in offices in Tokyo, Osaka, Nagano, and Sapporo. The main business focuses for JSOL are IT consulting, system integration, and computer-aided engineering packages such as JMAG. JMAG is sold globally through a network of distributors. JSOL handles the sales for JMAG in Japan, but distributors handle the sale of JMAG across the world. The distributor for both North America and Europe is Powersys Solutions. Powersys has been the distributor of JMAG since 2006 in Europe and since 2009 in North America. Powersys' main mission is business development, sales management, pre- and post-sales support of JMAG, promotion of JMAG at various events, and technical support and training services. Powersys also partners with JSOL to ensure that customers' needs are being met by providing feedback on what customers want from JMAG as well as what their experience in using JMAG is. So let's take a look at the JMAG product line. We'll start with JMAG-Express, which is a very basic way to set up a template-style analysis for a machine. So this covers most basic rotating machines and is it's easy to manipulate and modify in order to generate a simple motor analysis. We can also build motors or machines or any other type of electromagnetic analysis component using our link with CAD packages such as CATIA, SolidWorks, NX, and ProE. Once the model is constructed either in JMAG-Express or in CATIA, we can move to JMAG Designer, where we can do a full electromagnetic finite element analysis. We can also link to programs such as Abacus, where now we can do multi-domain analyses in structural, thermal, and computational fluid dynamics domains. JMAG can also use our JMAG RT Motor Model tool, which allows us to create a performance lookup table across the operating range for a rotating machine. These lookup tables can be brought in block form using our JMAG RT Viewer tool, which can help visualize performance across the operating range, in this case showing the efficiency plot versus torque and speed of a rotating machine. That RT block can also be brought into software-in-the-loop simulation programs such as MATLAB Simulink, PSIM, and Synopsys Sabre. We can also enter into hardware-in-the-loop simulation systems from companies such as National Instruments, Opal RT, and DSpace. JMAG Designer can also link with modeFRONTIER to run an optimization analysis, which is the focus of today's webinar. So let's actually take a look at creating the optimization model in JMAG. Our motor under investigation is an IPM machine with 2 magnets per each rotor pole. The IPM machine itself has a 112 millimeter stator outside diameter, a 55 millimeter rotor outside diameter. It's 37.5 millimeters tall, and its rated performance is at 1800 RPM, which is a 60 Hertz electrical frequency, and the rated torque is going to occur at a 7 amp peak current, which is a pure sine wave excitation at a 0-degree phase angle. Our model flow is like this, where we start by building the model in JMAG-Express and then exporting it to JMAG Designer for a full FEA analysis. In JMAG Designer, we can also link to our geometry editor, where we can now modify the geometry. The final step in this process is to set the parameters for optimization and the optimization conditions for the link with modeFRONTIER. So let's start at step 1, which is our JMAG-Express model. We first open JMAG-Express and choose the type of motor that we want to work with. JMAG-Express covers most of the common rotating electric machines such as IPM, surface permanent magnet machine SPM, brushless motor, outer rotor, induction machines, switch reluctance motors, brushed motors, and universal motors. Once we choose the motor type, then we select what type of rotor and stator configuration we want to work with, and then go through and set the conditions using our tabular format. So as you can see, the geometry tools, we can automatically modify the geometry, apply the different materials, apply the windings, and then set the drive conditions automatically in JMAG-Express. Once we've set the conditions, we can run a quick analysis. So this quick analysis can provide a rough estimate of machine performance. So effectively in JMAG-Express, we have a calculation setup that we can do in minutes and results that we can obtain in just a matter of seconds. Once we're satisfied that the results meet our minimum performance requirements, we can export the model to JMAG Designer to then run a full FEA analysis and obtain our baseline results. At this point, I'll pause and switch over to JMAG-Express and demonstrate that process. So if I open JMAG-Express, you can see we can select from our basic machine topologies. So in this case, this example is going to use a brushless motor IPM. We can either build a new combination by selecting the specific rotor and stator geometry, or we can select from some predefined geometries that have already been created in the Express library. So I'll select this geometry, which again corresponds to our 2 magnet per pole on the rotor topology. The default geometry that's brought up actually matches the geometry that we want to work with for the IPM machine, so no modifications to the dimensions are necessary. If, however, we wanted to modify the dimensions, it's very easy to set the new parameters. So we can, for example, change the number of slots on the stator very quickly, and I'll just change that back. Or we can go through and change any of the other dimensions in the geometry. Once our geometry is set, we can move to our Materials tab, where we can then choose the materials for the rotor, the stator, and the magnets. In this case, our rotor magnet is a neodymium iron boron with a BR of approximately 1 Tesla. We've applied that to both the first and the second magnet. And then our rotor core is going to be a 50A1000, which is a Japanese or a JSOL sheet steel. And that material is also going to be used in our stator core. But again, we can go through and we can access the entire JMAG material database to apply the materials for both the stator, the rotor, both the stator and the rotor, as well as the magnets. Once the materials have been applied, we can move to our Winding tab. In our Winding tab, JMAG will automatically determine the winding pattern based on the number of slots and the number of rotor poles. We can use either an automatic winding, an automatic concentrated winding, or we can manually set up the winding by specifying the input and output slot for the coil. Once the windings have been set, we can then move to our drive conditions. And in our drive conditions, this is the only difference actually between this model in Express and the model that we wanted to analyze for the optimization study. This model currently uses a voltage source. We want to switch that to a current source, and we want to change the peak amplitude from 3 amps to 7 amps. I also want to change the rotational speed from 3,000 RPM to 1,800 RPM. At this point, we can run the quick analysis by pressing the little light bulb button. As I said, the results are generated in just a matter of seconds, so it's a very good first pass approximation for machine performance. The results that we can view now are the torque versus current and the efficiency versus current, as well as the copper and iron losses, the DQ inductance, the phase voltage versus current, the torque constant, the average tooth flux density, and the rated current. We can also visualize the magnetomotive force. So once we get a machine performance that looks approximately correct or achieves the approximate results that we want to see, we can then click on our Calc and JMAG Designer button, which is then going to ask us to export a JCF file. I've already set up a folder on my desktop and exported the JCF file for this analysis, and so I'll just go into JMAG Designer and open up that JCF file. When the model is exported from JMAG-Express into JMAG Designer, all the settings have already been applied. Our assembly components have already been set. Our analysis conditions have already been applied for both all the phase coils, any periodic boundary conditions, the rotational condition, the torque condition, and any other boundary conditions that need to be applied. So effectively at this point, all that's left to do is right-click on our study and click Run Active Case. I've already run this analysis, and this will take maybe about 1 minute to 2 minutes, but I didn't want to slow down the webinar by going and having to wait that minute and a half for this to compile. So once we finish running the analysis, now we can view the results. So again, this is a full FEA analysis, which will give us some pretty comprehensive data as far as the material performance goes, or the actual machine performance. So now in our results, I can look at things like our average torque. So there's our torque waveform, and then our average waveform can be set by clicking on the average button. So now we can see how that is applied to create that average value. So I'll close that down. We can also look at contour properties such as the magnetic flux density, vector parameters such as, in this case, again, the flux density, or flux line plots. So again, coming in from JMAG-Express, we have a full and comprehensive FEA analysis capability in JMAG Designer. So now I'll step back into the presentation and we'll talk about what we're going to do for the optimization. So you can see we have our machine here, and what we want to optimize is basically the rotor magnet geometry. So the geometric parameters that we're going to pull out are the magnet thickness, the magnet width, the magnet angle, the magnet clearance, and the magnet position. The thickness and the width of the magnet, as well as the magnet angle, are pretty self-explanatory. The magnet clearance is the space between the center line, or the edge of the rotor, and the end of the magnet. And the magnet position is the position of the front edge between the front edge of the magnet and the origin of the rotation. Besides the geometric parameters, we also want to optimize the machine parameters, and for this we want to take a look at changing the applied current phase angle. To judge the quality of the optimization, we're going to set a couple of the output parameters. These are the average torque and the stator iron losses. When the model comes in from JMAG-Express into JMAG Designer, it has a default naming topology for all the dimensions that were used to generate the model. This naming convention can be a little bit hard sometimes, or a little bit confusing to go through and pick out the actual specific dimensions that we want to work with. So sometimes it helps to open the geometry editor and rename some of the CAD parameters in the CAD parameter list to more easily identify them when you're trying to set the conditions for the optimization. Once we rename them, if we want to, we then have to select the design variables. So when we select the design variables, now we're going to open the list of the parametric parameters available in the JMAG Designer analysis, and we're going to choose the parameters. In this case, I've highlighted our CAD parameters, which again are the angle of the magnets, the clearance between the magnets, the thickness of the magnets, the width of the magnets, and the position of the magnets. Once we've selected our design variables, we can then run the analysis. After we run the analysis, now we can set the response data. So we have to run the analysis in order to set the response data, because the response data is effectively the output of the analysis. So in order to generate the output of the analysis, we actually have to run the analysis. So when we select our response data, now we can pull out from all the other parameters or all the other data that we've achieved in our analysis. Now we can pull out the specific data points that we're most interested in. In this case, it's our torque, and I selected our iron loss and our iron loss on our stator and the iron loss on our rotor. In this case, we're not going to use the rotor iron loss, so it's a bit of a superfluous setting, but I left it in there anyway, in case we wanted to go back and add that to the optimization at a later date. So at this point, I'll step out of the presentation and go to JMAG Designer in order to do that demonstration. So now, I move into JMAG Designer, and this is effectively the same model that we got from JMAG-Express. I did make a few modifications, though, in order to more accurately capture the results. First off, you can see I changed the number of steps. The default coming out of Express is 33 steps. So I changed that to 65 steps to get a little bit higher fidelity, and to add a little bit more time. So then I could add a iron loss calculation to our conditions list. So the iron loss calculation will give us the stator and the rotor iron losses. I also made some modifications to the mesh. Typically coming out of JMAG-Express, the model in JMAG Designer will use an adaptive mesh, which means that JMAG is automatically going to determine the best mesh for this machine. But in this case, I wanted to come up with a little bit more control over the mesh, so I'm going to set a couple parameters on the mesh, such as an edge element size. Other than that, the model is fundamentally the same as what we got out of Express. Now, though, we have to go through and select our CAD parameters. As I mentioned, we can go into our geometry editor and we can change the names of some of the parameters. So again, the default naming scheme can sometimes be a little bit confusing, and you can see there's a lot of different constraints that we're going to have to sort through. So I can go through and by clicking on any of the the constraints, I can rename them to make them a little bit more easy to find. Once I've renamed them, now I have to go through and I actually have to select the CAD parameters that I want to optimize. So when we're setting our parameters for optimization, there's our main optimization list, but then there's also our CAD parameters that have to be selected separately. So I'll right-click on our CAD parameters and click on Select CAD Parameters, and this will give us all the constraints that we have that we just saw on the geometry editor. So as I said, sometimes there's a lot of constraints, so renaming something a little bit more familiar to yourself might make things a little bit easier to identify. In this case, I've selected the clearance between the magnets, the angle of the magnets, the thickness of the magnets, the width of the magnets, and the position of the magnets. So once I select those points, they're populated under my CAD parameters list. And so now this means that I can go through and I can actually click on Modify and then change the value. This value is actually grayed out since I've run the analysis, but if this was an empty analysis or if this analysis didn't have results, I could go back and change any of these dimensions and then apply them to my actual physical JMAG model. Once I've specifically called out the CAD parameters, I can now go and select all the parameters for my optimization. So I select all the CAD parameters that I've chosen, and then I can go through and I can select any of the other properties in this analysis for optimization. So I can change the materials, I can change some of the study properties, I can change the mesh properties, and I can change the conditions in my magnetic circuit. So in this case, I'm not going to change any of the coil conditions, but I am going to go through and I'm going to select the phase angle on that excitation current. So again, the default value is 0. We want to optimize this to determine the correct phase angle to give us the maximum torque point. Once I've selected the parameters in that parameters list, then I run the analysis and generate the results. Once I generate the results, if I look at the graphs and show the table, there's a lot of results to sort through. And so if I had to pick these out or go into modeFRONTIER to do the optimization and go through and kind of sort through the entire list of possible results, it would be a bit tedious. And so to make that easier, what we've done is we actually added the response data function, which means that we can take a value or a point sequence value such as torque and come up with an average value for our torque. And so you can see our average value for torque. Well, let's just take a look at that. So if I graph it, our average value is about 2.13 Newton meters. And so what I can do is I can actually go through in our tabular data, click Summary, and get that average value of torque, and then click on Response Data to register that as response data. I'll do the same thing on the iron losses, where now I'll click on Response Data and register my stator and my rotor iron losses as a response variable. When I register the response data, it's collected in this response graph in the response data folder. So now I can see that I've registered torque and I've registered my iron losses on the stator as response variables. So at this point, all that's left for me to do is click Save, and now I can move the model over to modeFRONTIER to do the full optimization on it. But before I hand the presentation back to Brandon, I just want to mention a couple things. The goal of this optimization is to minimize the magnet volume, maximize the torque, and minimize the stator iron losses, all while having a motor that achieves at least 2 Newton meters of average torque. Since this is an IPM machine, the magnet size and shape are going to play a significant role in the actual output performance of the machine. An IPM machine also derives its total electromagnetic torque from both a reluctance torque component as well as a magnet torque component. This means that since I have a reluctance torque that is actually a significant player in the total torque, that my actual peak torque as a function of phase angle is not going to occur at 0 degrees, as it would in a surface permanent magnet machine, but some other value other than 0. So when I add the phase angle to the optimization list, it means that we can actually achieve a peak torque that is the maximum torque that could be output based on the actual magnetic torque and the reluctance torque of this design. So now that adds a little twist to our optimization, but it also increases the range or the actual performance that we can achieve from this motor, as we'll see from the optimization. So I think at this point, what I'll do is I'll turn it over to Brandon, who will go and walk through the optimization from the modeFRONTIER perspective.
All right, hello everyone. As Dave mentioned, my name is Brandon Wagner with Stecca North America, and I'm going to be taking you through the process of setting up an optimization with JMAG through modeFRONTIER. And so we already went through the model a little bit. This is the model that we're using to run the optimization. And I'm actually going to show you two cases here. The first case, we had 4 design variables with 2 objectives. The design variables are magnet angle, magnet width, the position of magnets, and distance between magnets, with the goals of minimizing iron loss and maximizing torque simultaneously. As Dave mentioned, we'll have a constraint of that torque must be greater than 2 Newton meters. Okay, so using that problem statement, I can show you how we would set that up in modeFRONTIER. So I'll start this video demonstration, and you'll see my colleague Roel mentioned earlier briefly about the modeFRONTIER workflow. But what you see here is the modeFRONTIER GUI, the standard view. The main window there is the workflow window, and that's kind of the canvas that we will use to build our problem statement. So you'll see that in the video we go into our application nodes section and drop in a JMAG application node, and then we can specify our JMAG model that we'll be using. So once we do that, we can fire up what we call a parameter chooser, which actually is going to read the JMAG model using a modeFRONTIER script and pull out those CAD parameters that we specified in the model parameter list. So you can see here, once that's done, we have a list of variables that we can use and select that we would like to have in modeFRONTIER. Okay, so I'm going through and selecting magnet angle, magnet width, and things like that, and dragging them over into the modeFRONTIER output node, node window. And you can see here that we have a search function that can be useful for the output variables, because you might have quite a few output parameters being reported by JMAG. So we can search for iron loss and pick the correct iron loss value, and then click OK. And once we have those linked, you'll see that modeFRONTIER automatically builds our workflow. So as Roel mentioned earlier, we have a data flow going from top to bottom. So our 4 input variables are located above our JMAG process, and they're feeding into JMAG, and then we also have 2 output variables coming out of JMAG as our iron loss and torque. And then once we have that, we can go ahead and set up an optimization problem by dropping in objective nodes. So in this case, we have 2 objectives, so we'll have 2 objective nodes, each of which can be connected to our outputs. So in this case, we can tell it to minimize iron loss here in our expression editor, and then likewise we can tell it to maximize torque. Okay, and also we have that constraint of requiring torque to be over 2 Newton meters, so we can drop in a constraint node and set the constraint as torque must be greater than 2 Newton meters. Okay, and finally, we can set up our DOE, which will be the starting point of our optimization. In this case, we'll use a uniform Latin hypercube algorithm to populate our design space with an initial set of points. So you select uniform Latin hypercube, specify the number of designs you would like, and then say add DOE sequence, and it'll populate the table with the 15 individual designs that populate the design space in a uniform manner. Oh, I apologize here, the video seems to have restarted. Let me okay, and once we specify our initial population of points, I'll just let it go through here again real quick. We can select an optimization algorithm from modeFRONTIER's suite of algorithms. Each one has a slightly different approach. In this case, or for this example, we used 3 different algorithms in our optimization. and 3 separate optimization problems. But here you can see we selected our NSGA2 algorithm to optimize. Okay, so that's all that it takes to set up an optimization problem. We did this in just about 2 minutes, if you know what you're doing. So, okay, so this is our final workflow here. You can see I've modified the names of the variables to be shorter from what the names are in the JMAG model, and clean it up a little bit, but this is what our workflow looks like. So again, we have 4 input variables going into our JMAG process and 2 output variables. One is iron loss, the other torque, minimizing iron loss, maximizing torque, and constraining torque to be greater than 2 Newton meters. Okay, so in this case, we ran a direct optimization using our NSGA2 algorithm, which is a genetic approach, or genetic algorithm approach developed by Professor Deb. This is a good approach to fully explore our design space and avoids being caught in a local or optimum, or sorry, a local minimum or maximum, and can be used to find the global maximum. We also used a hybrid approach, which uses a genetic approach plus a derivative-based approach. So it runs a genetic algorithm, but a few designs will be calculating a derivative, calculating the direction of maximum slope towards your objective. So that derivative-based approach pushes the genetic algorithm toward the optimum a little bit faster than, say, an NSGA2 would. And finally, we also tried a FAST strategy, which is, again, a genetic approach, but it's infused with a response surface-based approach, meaning that we train a response surface approximation of our output, which will then be used to run a kind of interim optimization, which will then push the optimization algorithm faster than a standard NSGA2 approach would. And for each iteration, this response surface is improved upon in an iterative process, and eventually pushes the optimization much faster than our standard approaches would. Okay, and I'll show you a case or an optimization with each one of these approaches. So we had, in case 1, we're using NSGA2 with 15 initial population, which actually might be a little bit overkill in this case with 4 variables and 2 outputs. And for each evaluation, it took 90 to 120 seconds on our workstation. And this time actually just depends on the amount of time it takes to evaluate your JMAG model independently of modeFRONTIER. But this is the amount of time it takes for each evaluation with modeFRONTIER as well. We didn't use any concurrent evaluations, meaning that we only ran one JMAG model at a time. However, it is possible to run concurrent evaluations if your licenses allow it, or if your hardware allows it. So in our case, we ran a single design at a time, and we evaluated 1,000 designs with NSGA, about 67 generations of 15 points each. And this took about 29 hours total. So this takes about a full day for an optimization using this number of generations. However, you'll see also that it's not necessary to run quite so many in this case. And it is possible to stop before that 1,000 points is fully through. Okay, so here, this is the results of our optimization. In a multi-objective case where the objectives are competing with each other, such as this, is a standard approach to view our objectives versus each other. So on this chart, it's a standard 2D scatter plot. You'll see iron loss on the x-axis and our torque on the y-axis. So keep in mind that we want to minimize iron loss while also maximizing torque. So we want to move along this direction of the graph and simultaneously move along this direction, and hopefully reach this point here, which is what we call our utopia point. Now the physics of the problem may not always allow you to reach that point, as you'll see. But in this chart, you can see these white points here consist of our initial 15 uniform and hypercube designs that we used. and you can see that they are all located closer to the lower right-hand portion of the graph. And each of the blue points represents a point that was determined by NSGA2 as a search to search for an optimum design. So we can call each of these points located in the lower right dominated point because there are designs that represent an improvement in each of the objectives at the same time. So as you move from this point here, which is a DOE point, to this point, which was found by NSGA2, you see that we have decreased iron loss and increased torque. So we call these points dominated, and then eventually we will reach a frontier, or what we call a Pareto frontier, which represents the best designs as far as a combination of torque and iron loss. So each design on the Pareto frontier will represent an optimum combination of those two variables. And it's not possible to improve upon both variables at the same time. So you can see here, we can pull out just the optimum set of designs called the Pareto front that NSGA2 determined. So you can see that we have sort of a convex shape here, which has a strong curve near the left end and then kind of tapers off toward the right end of the graph, where torque increases slightly and iron loss increases drastically. Okay, so I can show you kind of a progression of how the NSGA2 algorithm worked. So this is a scatter of points that NSGA2 found after 200 designs. So this is about after 6 hours of runtime. You can see that the Pareto front is starting to form, but it's not quite as full as after the full run. But it's starting to improve upon the original 15 points drastically here. And after 400 designs, you can see that the Pareto front is becoming even more defined. Still a little bit broken in some points. Again, this is after 12 hours, and then after 600, you can see it keeps progressing, keeps filling in that Pareto front. And after about 800 designs, you can see it's just about fully explored that Pareto front with a couple of gaps here. And then finally, after 1,000 designs, this is what the algorithm came out with. Now our next optimization case, we ran hybrid on the same problem. Again, 1,000 designs, about 29 hours total, with the same 15 initial points. And you can see this is the final results of the optimization study. You can see actually our baseline design that Dave showed you earlier is located on this point in the graph, so it represents a very high iron loss compared to most of our optimum designs and a lower torque. So you can see that the optimization algorithm improved upon both of those objectives. So the difference between hybrid and NSGA, again, the hybrid is using the derivative-based approach to speed up the convergence of the optimization. And you can see the effects of this, that more points are concentrated along the Pareto front compared to the NSGA algorithm. So here are the Pareto points. Again, this is the set of optimum points that the optimization algorithm determined that we can choose from. And again, we have a progression here. After 200 points, this is what the optimization looked like. And then after 400 points, or 400 designs, you can see that the Pareto front is beginning to fill out more here. And at any point in this optimization, if you determine that that you're dissatisfied with the designs, you can always stop it and pick a point along this Pareto front. You can see that they've already improved much upon the baseline design here. And then finally, we ran a third algorithm here called FAST. Again, this uses a response surface to approximate your output and speed up the optimization. And here you can see a clear difference that almost all of the points are concentrated along this Pareto front, which is good. After 200 designs, you can already see that the Pareto front is pretty well defined, where compared to the other algorithms, it was not quite as well explored or even found yet. This is clearly our best case running the optimization here with the FAST algorithm. And after 400 designs, you can see it is pretty much fully populated this Pareto front, whereas it took maybe 800 to 1,000 for NSGA and maybe about 600 for hybrid. So this can show you that using a different algorithm can drastically improve the speed at which you converge and the amount of which you explore the design space. So here you can see that there really wasn't much benefit of running up to 1,000 designs. You probably could have stopped after 400 and gotten the same results. So again, this running 1,000 designs might be a little bit of overkill in this case, but just to show you how our algorithms progress. And now I can show you a direct comparison between the algorithms. So we have NSGA2, the full of the 1,000 designs here. I can overlay that with our 1,000 hybrid points. And you can see that maybe hybrid has a bit better concentration near the optimum, especially around this region. And then finally, we can compare that directly with FAST, which is clearly much better because it concentrates nearly all of the points near the Pareto front and has much fewer dominated points in this region of the graph, and it reached that much quicker. Okay, and just to give you an idea of a visual representation of what these designs look like, we have here in the lower left corner, we have that same 2D scatter plot with a baseline design marked here, which is shown up in the upper left corner. So you can see this is the design configuration with the magnet angle of 120 degrees, the width of the magnet at 14 millimeters, the height of the magnet, the position of the magnet at 11 millimeters, and the distance between them at 2.5 millimeters. In the upper right corner, we have what we call a parallel coordinates chart, which is another post-processing tool of modeFRONTIER. The red line, or each individual line here represents a design from optimization. So this chart shows the full 1,000 optimization designs, and the baseline design here is marked in red. So you can see how the design, what the design parameters, what ranges they have within the full range of values for that design. So you can see that for the width of the magnet is concentrated near the higher end, the torque is near the higher end as well, and is also the iron loss near the higher end of the full data set. So I move along, if I look at a point along this part of the Pareto frontier, we can see that the design looks drastically different as far as the magnet angle. It's now about 60 degrees rather than 120. The width of the magnet has shrunk a little to about 13.5 millimeters. The position of the magnet is now 9 millimeters from the center, and the width distance between the magnets is about 2 millimeters. So this is considered an optimum design determined by our FAST algorithm along this point of the Pareto frontier. So this has a very low iron loss compared to the baseline design and a little bit higher torque. So now we can look at a design at a different point along the Pareto front, located here. So this has a little bit higher iron loss and also higher torque. So it improved along torque, but it is a little bit worse for iron loss. But you can also see that it has a very similar design, except the magnets are a little bit closer to our stator here. And you can see for a design along with even higher torque and higher iron loss, it moves even closer to the stator. So you can determine that the optimum configuration for this set of parameters for basically the magnet angle is being pushed to a 60-degree angle, which is a lower end of our input variable range. And the other parameters don't matter quite as much, but as you push it closer to the stator, it increases your iron loss, but also increases your torque. So we ran another case. So this has a full 6 design variables that Dave showed you. In this case, we added the variable for the thickness of the magnet and also the phase angle of the current. We also added an objective to minimize magnet volume simultaneously with maximizing torque and iron loss, and we kept the constraint for keeping the torque above 2 Newton meters average. So this workflow is very similar to the one I showed you before. However, we've just added the thickness variable to the workflow, and then an objective on it as a combination of the width of the magnet and the thickness of the magnet, and then the phase angle as an input variable. And this can be done in literally a matter of seconds in modeFRONTIER. So it's very easy to create a new optimization problem or statement. In this case, we ran the same 3 optimization algorithms, NSGA2, hybrid, and FAST, and also ran a design of experiment study using a uniform Latin hypercube. So this is in this case, we ran a large number of points using a DOE just to explore our design space in a uniform manner, and from there we can perform a sensitivity analysis and determine the effects of our outputs, of our inputs on our outputs, and then also train a response surface to attempt to approximate our outputs, and then we can use those to run what we call a virtual optimization using an approximation model. So in this case, we ran, instead of 1525 uniform Latin hypercube DOE points, and again, this may be a little bit more than you run if you're on a time crunch, but in general, the more variables you have in your workflow, the more input variables you have, the more DOE initial population you will want to run. You could probably, in this case, get away with running about 15 for a 6-variable case. And again, we ran about 1,000 points total. Again, this took 29 hours. And you can see here, now since we have a third objective, we'll use a slightly different way to look at our output data. This is what we call a bubble chart, which is a standard 2D scatter plot, but it has a third dimension added as a color gradient of the bubbles. So our the color gradient represents the magnet volume. A red color represents the high range for magnet volume, in this case around 35 millimeters squared, and the blue color represents a lower magnet volume. So you can see that our full design set looks a little bit different, but we have a trade-off here between iron loss and torque again, and then we also have a trade-off with magnet volume. So we want to reach this end of the graph again, but also with a low magnet volume, or a blue point. So if I mark our optimum designs in modeFRONTIER, which is a very easy process, I can pull out the Pareto set, or our optimum set of designs. And you can see that we have a clear trade-off between torque and iron loss, and then also magnet volume. So this is actually Pareto's surface now, because we have 3 objectives which all trade off with each other. And you can see our baseline design is over here, so it's dominated by each of the points in the Pareto set. So we can conclude that our optimization algorithms were able to pull out a good set of designs here. So again, we ran hybrid with the same configuration, 1,000 designs, and after the full data set, you can see we pull out our Pareto points, and it distributes them a little bit more evenly throughout that Pareto surface, again with our baseline design dominated by those points. And finally, with our FAST algorithm, you can see that now we have actually a much greater spread of points overall, and the Pareto set is much more finely distributed, so you have a greater set of points you can choose from that are considered optimum designs. So here is a side-by-side comparison of each of the algorithms. You see that FAST-NSGA, again, has a much better spread of points, which is the goal. So in this case, we would also recommend running FAST-NSGA for this type of problem. And here we have a comparison of each of our 2 cases with 4 design variables and 6 design variables. in this case, I'm showing the FAST algorithm determined points. And here we can see that Pareto front for that first case is actually dominated by most of the points in our second case. And that's because we added our freedom of modifying phase angle and magnet thickness. So that can show you that adding some variables to the design variables to your model can drastically improve your results. So most of these points here would be considered Pareto for FAST, and they represent an increase in torque and a decrease in iron loss from our first case. Okay, and we're running a little bit short on time, so I won't go through the DOE study too much, but this is another post-processing tool that we use called scatter matrix, which can be used to determine the effects of our inputs on our outputs, and you can see general trends that our inputs have on our outputs, whether they're directly correlated with, say, torque or iron loss, or inversely correlated with torque or iron loss. And we can train response surface models using that data set, which approximate our output, and then we can run what we call a virtual optimization, which is an approximate optimization here. As you can see, this using the virtual Pareto, it's very similar to our real set of designs determined by our FAST algorithms, and this can be used to quickly determine a approximate optimum design. Okay, so conclusions from the study. FAST-NSGA provided the best Pareto front and the fewest amount of designs in each case, in our 6 design variable case and our 4 design variable case. The Pareto frontier obtained from the 6 design variable case dominated the Pareto frontier obtained from the 4 design variable case because we added more freedom to our model. And finally, a small initial investment in building the modeFRONTIER workflow, automation workflow, can provide considerable value in terms of design improvement through optimization. So each of these studies was run in the course of a day, and it could be run in the course of even less than that if you ran concurrent designs, and if you decided to stop your optimization before 1,000 designs, which quite frankly was a little bit of overkill. And now I'm going to pass it over back over to Dave, who can explain some of the other benefits you'll see from running with modeFRONTIER.
So, okay, we'll transfer the control over to Dave.
Okay. So hopefully you can see my screen. All right, is it or is
yes,
the screen just excellent? All right. Well, yeah, with the optimization, if we look at the initial model parameters, we see that the geometric parameters are as Brandon mentioned, and our machine parameters are as we discussed before. The performance of this baseline model, our average torque was 2.13 Newton meters. Stator iron losses were about 14.2 watts, and the magnet volume for a single magnet is about 1050 millimeters cubed. Our initial results show that our torque versus time, we have a peak-to-peak torque of approximately 0.5 Newton meters, and again, the average value about 2.13 Newton meters. And I also plotted the flux density to show the saturation in the stator teeth. You can see that there's actually, the red shows a high flux density, and we can see red and orange, a lot of red and orange in the stator. So we're actually pushing a fairly high flux density into the stator teeth. So from that basic design, I was able to go back into JMAG, then just duplicate the study, and then create the new study for the minimum magnet volume, the maximum torque, and the minimum losses. So effectively the optimal value for each of the 3 parameters that we were trying to optimize. And then I was able to go through and run the analyses and pull the results from each of these models. So now with JMAG, again, we have a little bit more freedom to look at what are those differences, why are they occurring, and get a little bit more information than just the average torque and the average loss. So now if I look at the minimum magnet volume, again, this is the actual geometry that we were looking at. Performance on the minimum magnet volume, the average torque, about 2.15 Newton meters. Stator iron losses, 12.2 watts, but the magnet volume nearly cut in half from our initial design. However, if we look at the peak-to-peak torque, we can see it's a little bit tighter, but at the same time only about a 0.5 Newton meter spread from the peak to peak. On our flux density plot, this is where we're going to see some differences. So now, how much red and orange there were on that initial plot, we're seeing a lot less red and orange. So it means we're pushing a lot less flux density, through our stator, but still achieving about the same amount of average torque. So again, better utilization of the materials in this case to generate the output performance properties. In our maximum torque case, again, it changed the magnet width, or it changed the magnet angle a little bit and a little bit of the magnet width. But now we're getting an average torque of about 3.91 Newton meters, almost twice the average torque. Stator iron losses, again, are still almost 4 watts lower, and our magnet volume is only slightly higher than in our initial case. Again, if we look at the flux density, the torque waveform, I'll start there, we see that the peak-to-peak torque is approximately 2.5 Newton meters. So in order to generate that higher average torque, now we have to get actually a fairly big swing in our peak-to-peak torque. So that shows us the trade-off. If you were just to go back and run off the optimization and say, well, this is the design that's going to give us the maximum torque, we might neglect the fact that that trade-off is that the average torque is high, but the peak-to-peak torque is also significantly higher than in our initial case. So this torque variation might not be acceptable in the machine design. However, in some cases, perhaps the peak-to-peak torque differences, that is an acceptable trade-off to get a higher average torque. We can also look at the flux density plot in the stator teeth and again see a big reduction in the amount of red and orange in the stator, which again leads to a lower iron loss. In our minimum loss case, the magnet angle actually increased, and then the width of our magnet decreased a little bit. And our average torque goes down just below the threshold, but our stator iron losses are at 7.46 watts, are nearly cut in half from our initial iron loss estimate. Our magnet volume is also only slightly higher than in our default case. And we can see if we look at the minimum loss results, our peak-to-peak torque now goes from about half a Newton meter in our initial default case to about 0.4 Newton meters. So it's actually a tighter peak-to-peak torque generating the average torque. And if we look at our flux density plot on our stator, there's nearly no red or orange. It's all greens and yellows, which means it's a very low flux density in our stator, which again leads to a much lower iron loss result. Pulling all 4 of the designs together, we can see that optimized designs can have significant differences between themselves and the original model. And by using modeFRONTIER, it becomes easy to select which parameters to optimize or choose different parameters based on what type of results that you want to look for. Another thing that I want to mention is that it's also possible to have equation-driven parameters. So if we wanted to limit the magnet volume to a certain physical value, we can change the magnet width and the magnet height to correspond to that exact magnet volume. And so those equation-driven parameters are also a possibility. As far as my conclusions go, by optimizing the design, it is possible to achieve at least 2 Newton meters of torque while cutting the magnet volume in half, or doubling the output torque, or cutting the losses in half. So to achieve these results requires testing alternate geometries and excitation conditions, which, as mentioned by Brandon, there were up to 1,000 cases tested. So it can be easily done with an optimization tool, whereas by going step by step and trying to do it on your own or independently might be time prohibitive or nearly impossible to do. So I think at this point, that concludes our presentation, and I think we can open up the floor to questions, but I'll turn that back over to you, Sumit.
Okay. So sorry we have gone a little bit over time, but at this point we can officially conclude the presentation part, but we'll keep the floor open for questions. So before we do that, Abdul, if you just want to give some final comments about the user meeting and contact information.
Yeah, thank you, Sumit. As you can see on this slide, if you have any questions for either JMAG or modeFRONTIER, here are the company's contact information on the screen. And also would like to take the opportunity to make you aware that we have our North American users meeting coming up in the first week of November, located here in Plymouth, Michigan. So if you would like more information on that, you can go to our website or contact us through the emails listed here. So I'd like to thank you for the attendance, and then with that, I would like to open it up for some questions if there are any.
Okay.